All right, so now that we know a little bit about the shape of molecules, we got to talk about the polarity of those molecules. So this is kind of takes all the things that we've talked about and combines them all together. So it can be kind of complicated, but it really shouldn't be that hard. You just kind of follow a process to get your answer when it's all said and done. But we do have to worry about the polarity of molecules because, as you can see in your notes here, molecules with similar size can show a wide range of properties. So when you compare methane and water, right? So methane being that CH4 and water being H2O, as you can see, those two molecules have very different properties, right? They're actually similar in size. One carbon plus four hydrogens is about a mass of 16.05 AMU. Two hydrogens and an oxygen, that gives me about a 18.02 AMU mass. And so they're similar in size, but methane is a gas at room temperature and water is a liquid. And there's a big reason for that, right? We know that water is very polar, that water molecules attract each other, right? We spent a good chunk of biology talking about how those water molecules, right, can attract one another because there's hydrogen bonding between the oxygen of one water and the hydrogen of another, right? But the reason for that attraction is there's a separation in charge. When you have an oxygen and a hydrogen bonded together, that oxygen pulls on electrons more effectively than that hydrogen, so the hydrogen ends up with a partial positive charge. But the same thing's happening in both molecules. So this negatively charged oxygen is attracted to this positively charged hydrogen. And those oxygens are even doubly negative because they're stealing electrons, pulling on electrons from two different hydrogens at the same time. But water can only be polar because it's bent, right? Methane, on the other hand, that CH4, right? If I drew that molecule out, remember it's going to be tetrahedral. And although in this case it doesn't actually matter that it's tetrahedral, sometimes it does, right? When you have those hydrogens spread out equally around that carbon, sometimes they can, right, polarity can cancel out. And we'll talk about that in these notes. But in this case, it's actually a simple case of carbon is 2.1, or excuse me, carbon's 2.5, hydrogen's 2.1. If I subtract those two things, I only get a separation of 0.4, which meant that they're nonpolar bonds in this molecule to begin with, right? But again, sometimes that 0.4 is not really the boundary, right? It depends on what book you're looking at. But even if there were polar bonds in this molecule, that methane molecule, it would likely be nonpolar anyway, right? But it's the fact that it's nonpolar that means that it's not going to be a liquid at room temperature. It's not going to attract other methane molecules very easily, like the water can attract another water. So the polarity of these molecules and their shapes and how the shape affects the polarity are going to be a big deal in terms of properties. So we need to learn a lot about that, right? Otherwise, aside from just their physical state, right, water being a liquid, methane being a gas, you can have other situations. Sugar dissolves in water because both sugar and water are polar substances, right? But oil, any kind of oil that you're talking about, whether it's like oil in an engine or like cooking oil, right, is very nonpolar. So it doesn't mix with those polar things. So when you have substances that dissolve in other substances, the only way they can do that is if they're like that other substance. Polar dissolves polar, other polar things, whereas nonpolar only dissolves other nonpolar things. polar and nonpolar do not mix very well. So again, we're trying to figure out the polarity of these molecules, and it can be kind of difficult, right? But it does depend on the shape. So again, it says that there's a table here. This is the point where you might need a worksheet from your sub, right? A worksheet that looks something like this. So I'm going to go through some examples, but I'm also going to I'll just go through like the first 4 examples on this thing, the methane there, that dihydrogen sulfide, carbon dioxide, carbon tetrafluoride, right? So I'll just do the first 4 examples on there so that you know how to start, and then you just can go from there and see how many things you can figure out, right? How much you can figure out. So, like I said, I'm going to go through those examples. The first one we've already done technically, but remember this is a process. You're not always going to be able to jump right to it the way that I did, right? The first step, actually, when you see this CH4, is to figure out, okay, how do those things bond together, right? So you're supposed to know that carbon can make 4 bonds. You're supposed to know that each hydrogen can only make 1 bond. And so intuitively, you'd probably put the carbon in the center, but there are different parts of this process, and it depends on where you're at in this learning curve, right? Maybe you can jump directly to tetrahedral. You knew that that was going to be tetrahedral right away. Maybe you have to go through the process. Maybe you have to connect all those dots and then realize, oh, carbon has 4 bonds around it. That sounds like a tetrahedral shape, right? Maybe even you would want to use that simulator like I used before. Add 4 bonds like this, right? And you'd say, oh yeah, that's that tetrahedral shape we were talking about, right? So it depends on how you start, right? You might have to connect the dots first, but then you clean it up and you draw it with the appropriate shape that we talked about before. So you have to try to draw that tetrahedral in a way that represents that 3D shape. So it should look something like this. One thing I would suggest, if you're a little sloppy with your drawing early on and I'm not going to be able to tell that that's tetrahedral, you might go ahead and put a little label next to it. Just tell me that it's tetrahedral, right? Just in case, because maybe I can't tell what you drew. Again, I do want to make sure that at least this bond angle that's in plane is bigger than 90, right? So I can get credit, because otherwise if you're not following the detail-oriented parts of this process, right, you're really not going to be able to understand what's going on. It's impossible to know what's going on if you can't do those details appropriately. But then finally, right, I try and figure out, is this thing polar or nonpolar? The first thing I do is I think about, okay, these are all carbon to hydrogen bonds, right? And then like I did just a second ago, I subtract 2 values. 2.5 minus 2.1, I get a 0.4. Right, that tells me right away that those bonds are nonpolar. If the bonds are nonpolar, then the molecule is automatically nonpolar. So that's just what it is, right? There's a flowchart up here on my worksheet that says if I have nonpolar bonds, any shape is going to be nonpolar, right? So you don't have to make it harder than it is. Once you have nonpolar bonds, I know that this is a nonpolar molecule. So next to the molecule that I drew, I need to say nonpolar, but also I need to say that it's nonpolar because the bonds are nonpolar, right? Which is actually going to be important here in a second, because there are different ways that a molecule can end up being nonpolar, and it's not always the bonds. So that's just one example, right? Our next example apparently is that 2 hydrogens and a sulfur. And again, it depends on where you're at in this process. How good are you at it at this point, right? If I had 2 hydrogens and a sulfur, you might be able to jump to a shape right away, but maybe you don't know what shape it's going to be, which most of us wouldn't. So I figure out, okay, sulfur's in group 6, so it's got 2 single electrons. Hydrogen has 1 single electron. Okay, I'm probably going to connect it together here and here, right? And then I got to think about what shape that is, right? that should actually be kind of familiar because it kind of looks like water. But if you didn't know, like I said, you could use the simulator. Make sure you have two bonds, right? But it's not just two bonds. There's also two pairs of electrons. When I add those two pairs of electrons, you should recognize, oh, this is that bent shape that we were talking about before. This is something that I definitely can draw in plane. My picture actually already kind of looks bent, right? But I should clean up my picture, right, when it's all said and done. I do need to make sure that this bond angle is slightly bigger than 90, right? But this is a bent shape, and I might write bent next to it just in case. But now I want to know, is this a polar or non-polar bond? Or molecule, excuse me. But I do look at the bonds first. So I have to actually go backwards here because I got it in the notes. Otherwise I don't know where it is. Where was that thing? Oh, here it is. Okay, click on the electronegativity chart. So I got sulfur is 2.4 and hydrogen is 2.1. Excuse me, I'm going the wrong way here. 2.4, 2.1. So I just subtract those. Again, I don't really have to do that, write it out. I can tell in my head that's 0.3. I can tell in my head already that, okay, that means this is going to be nonpolar, right? They're nonpolar bonds. So this one actually has the same answer as the last one. This is definitely a nonpolar molecule because the bonds are nonpolar. And again, you have to tell me why it's nonpolar. You're actually going to miss points if you don't tell me why. So then my next example is a carbon dioxide. Right, again, you may or may not know what the shape is right away, but at a certain point you're going to get to a state where you're thinking, oh, I've done that example before. I know exactly what shape it is, right? I don't care if you skip steps in this, but you do have to do certain things at all times. If you know right away that this is going to be linear, that's great, right? Like I said before, if I have, let's get rid of everything, two double bonds to two oxygens, and no pairs of electrons, I'm definitely going to get a linear shape, right? But you might have to go through the whole process. You might have to have the carbon with 4 dots, and you have the oxygens with 6 dots, right? And you're trying to connect dots to make everything happy, right? And you realize, oh, that carbon's going to be in the middle. I'm going to have these 2 oxygens that are double bonded to a carbon. Then you clean it up and say, okay, yeah, that's definitely going to be linear. I do want to see dots on answers. It's the pairs of electrons on the central atom that matter the most, but I need all pairs all the time, right? If I did add a pair to the central atom, I'd get a whole new shape, right? And this shape actually is a different version of bent again, right? That would also be kind of weird. I don't know of any molecule that looks like this one, but pairs matter, right? Especially the pairs on the central atom. So I know that this is linear, so I'm going to write linear. But otherwise, I want to know if this is polar or nonpolar, right? I do happen to remember that oxygen is 3.5 and carbon is 2.5. So when I subtract those, I get 1.0. That's bigger than 0.4. So that's definitely a situation where those bonds could be polar, right? So what I have to think about now is my shape in those bonds, right? Is this thing going to be polar or not, right? And this is actually one of the best examples to represent the next concept that we're going to talk about, right? Since oxygen pulls on electrons better than carbon, this oxygen is going to try and pull electrons in this direction, right? Don't draw these arrows yet because you might not want to. This oxygen is going to try and pull electrons in this direction. Now, understand that both of them are trying to pull electrons from that central carbon, and they're pulling in equal and opposite directions. This chart that I gave you, right, this little graph, or excuse me, it's a table that I gave you at the top up here, right? It says that if you have a polar bond, right, there's 2 different possibilities. You might have a canceling shape or a non-canceling shape. If you happen to have a canceling shape, you're going to have a nonpolar molecule. And canceling shapes are linear, planar, tetrahedral. This example is definitely a linear shape, right? If you have oxygens that are trying to pull in opposite directions, they're actually going to cancel each other out, right? They try and take electrons from that carbon, but they're actually pulling against each other, and when it's all said and done, nothing's going to happen. This is a nonpolar molecule, actually. And it's nonpolar not because the bonds were nonpolar. The bonds could have been polar, but there's going to be a canceling situation here. So you have to tell me that. It's nonpolar, but it's nonpolar because it canceled. Right? So there's two different possibilities for nonpolar. It could be nonpolar because the bonds are nonpolar, or it could be nonpolar because it cancels. But you need to determine which is which. Right? Our last example for now, that carbon tetrafluoride, and then you guys can practice on your own. A carbon tetrafluoride, I'll change black here. And again, you might already know what shape this is going to be because you can intuitively think of that every once in a while, but sometimes you have to work it out. So I know carbon tends to make 4 bonds. There happen to be 4 fluorines. All 4 fluorines can make 1 bond. So I'm guessing that the carbon's going to make 4 different bonds to 4 different fluorines. I could skip a step if I want to and go directly to my shape, right? My shape in this case with 4 bonds is going to be tetrahedral. So I got up, a little bit down, out towards me, back behind, and I have fluorines surrounding this carbon. But I have to be careful because all these fluorines should have pairs of electrons on them. I'm going to take points off if you don't show me all the pairs, because some pairs matter, some don't. But until you know the difference, you have to draw all pairs all the time. So the fluorines are all going to have 3 pairs of electrons on them. The central carbon has no pairs though, right? Because again, it's going to be tetrahedral. So I might draw that out here. I might say that it's tetrahedral just in case. So next step, I want to know if this is polar or nonpolar. If you look up fluorine on your electronegativity chart, it's actually a 4.0 or 4.1, I don't know. 4.0 subtracted carbon. This is definitely going to be a polar case though, right? So those would be polar bonds, but again, you have to think about the shape. And you actually might use that table that I gave you, right? Tetrahedral is a canceling shape. So although there could be polar bonds in here because these fluorines are pulling in equal and opposite directions, right? It might be hard to tell, but those 3 fluorines that are pulling slightly downward are canceling out that 1 fluorine that's pulling straight upward, right? So it's not as easy to tell because you have to understand how those forces are distributed throughout that molecule. But as long as they're spread out evenly, as long as it's a linear shape, a tetrahedral shape, or even a planar shape, right, you're going to have canceling. So this is going to be another nonpolar molecule. But again, it's nonpolar for a reason. It's nonpolar because it cancels. I'm having trouble with my pen right now. So as you can tell, I've already done 4 examples, and they're all nonpolar, right? The only example that was polar so far that I talked about was water. But water has a bent shape, and bent is one of the examples for non-canceling shapes. So as long as it's bent or pyramidal, you might have a polar molecule. If it's not one of those 2 shapes, it's usually nonpolar. But you have to be careful too, because all I have to do is change one little thing, and it's all different, right? If I made one of these fluorines a hydrogen, this would no longer be nonpolar. Because the only way something can cancel is if I have poles, if I have forces pulling in equal and opposite directions. If I had fluorines down here pulling away from that carbon, and I have a hydrogen up here, the hydrogen doesn't pull electrons better than carbon does. Carbon actually pulls electrons better than hydrogen does. So this actually would be a polar molecule when it's all said and done, right? The bottom half of this molecule would be more negative and the top half would be more positive. I see a dipole overall. This is definitely a polar molecule. That's something that you have to be able to do in a polar molecule. If I have an oxygen and two hydrogens, we know that water is polar, right? But it's polar because you can separate positive and negative. I can even draw a line here that separates my positive hydrogens from my negative oxygens. But when I had that carbon dioxide, if I tried to put those if I tried to put those arrows in there saying the oxygen's more negative, the carbon's more positive on both sides, right? I can't draw a single line to separate my positive and negative, right? I actually would have to draw a line that curves to separate positive from negative, right? So I can't do that. This is not a polar molecule for that reason, right? I should always be able to draw a straight line that can separate one region that's positive from a region that's negative, right? But it only works for things in certain scenarios. Right? This actually would be a polar molecule up here if it was a hydrogen instead of four fluorines, and in that example we had previously. Right? This is a polar molecule, but this is nonpolar because I can't separate those charges. If you do get a polar molecule, you are supposed to draw it appropriately. So when I had water, right, I don't actually say that it's polar, remember. I actually just go ahead and draw those symbols that indicate that polarity, that tell me that the charges are separated, right? Whereas I would not put those things on something that's nonpolar. So when I did my carbon dioxide example before, this answer here did not have any arrows on it. It didn't have any partial positive, partial negative. It shouldn't have any of those things. But if you have a polar molecule, you should include those, right? Everywhere they're appropriate. Okay, so that should be plenty of examples to work off of. Just finish that worksheet the best you can, and you can ask questions when I come back Wednesday.